maybe affect the excitation of the nucleons that are speeding out, and may, for instance, excite the delta levels, which is excited to the M1.
Yeah, the first one is, these are the smallest mass vector mesons, so they are more abundantly produced. So we have not looked at higher because this is already statistics hungry. And the second part, Jepsi, yeah, Jepsi we have started looking at. And on the second part, the magnetic field dies down very fast. So by the time things hadronize and those excitations, this initial magnetic field is not there. But if the medium is conducting, then it may capture some effect. But then what is the conductivity of a quark-gluon plasma is again has to be figured out. Then only it can retain some effect maybe.
Okay, the last question. You have this. Hello. Yeah. No, just please.
Yeah, my question is regarding the vorticity. In normal fluid, this vortices breaks down, right? I mean, in the turbulent flow. So, does this kind of observation, something sort of like this happening over here also?
Yeah, so that would need a full-fledged relativistic spin hydrodynamics. But this simple-minded translation that if the full polarization gives rise to the entire thermal vorticity, then you can make a connection. But those details would depend on how system evolves hydrodynamically. And that is a sort of area which is being worked on.
Okay, so last.
But the fluid is very highly turbulent in this.
I now don't remember the Reynolds number values which is extracted, but I can later on check and let you know. I'm somehow not getting the number which people have tried to.
Maybe the flow is compressible, not incompressible.
Angular momentum is conserved. You
Yeah.
get rid of vorticity completely. So that is the thermal limit.
Okay. First.
So I just wanted to make a comment following up on this discussion as to which temperature one should use. We know that the magnetic field falls off very quickly in time, and we know that it takes some time to establish at least enough equipartition of energy so that hydrodynamics is applicable. We know that's fast. We don't know exactly why it's so fast. However, it's not instantaneous. So I think there's a big uncertainty as to which temperature one should put in there and which magnetic field at the time.
Okay, so let's thank Vedant again for a lively talk and lively discussion. So now, is Rolf there or not? Yeah. Okay. So our next speaker is Rolf Hoyer, the former DG of SAR. And we remember last time we had Rolf in India. That was a talk that he gave at Electron Photon in 2011, which session was chaired by Professor Vikas Sinha, and I was the organizer or chairman of the Electron Photon that year. And now the role reversal. Professor Vikas Sinha is the chairman of the organizing committee, and I had chaired in Rolf's session. Rolf, so.
Good morning, can you hear me?
Yes, we can hear you.
Yeah, I tried it, but it doesn't want.
So your camera is on or we are not seeing it?
It always goes on, so I don't know what. No, my camera doesn't switch on.
Yeah, but we have not.
So shall we go straight to the top?
That would be perfect, yes.
Yeah. So let's go to the top. So you'll be showing the top from here? Local or not doing it from remotely?
I would prefer to do it myself.
Okay, great. So you can go ahead. Share the screen.
But where is it? How can I share the screen? Present now. Yes. Okay. Okay. Good. Can you see it? Okay, now I have to go to presenting now. Okay.
Great.
So, good morning everybody. It's my great pleasure to present a sort of overview talk concerning CERN today, CERN tomorrow, and something which I find very important is the role of large infrastructures for a sustainable future. Well, let me start completely differently than I do in other cases. We are here at the international conference, and I like the title Macrocosmos, Microcosmos, Accelerators and Philosophy. Celebrating inter alia the 160th anniversary of the birth of Rabindranath Tagore. And I think yesterday you had a presentation on the discussion between Tagore and Einstein. And that's here, I think it was 1930, when Einstein and Tagore met in Berlin and explored the friction between science and religion. I'm asking now, is there really only friction? Or isn't there something else? Aren't there commonalities, overlaps? Can one learn from the other? And I looked through the songs from Rabindranath Tagore. I looked through Gitanjali. And when I read number 35, I must say I was first of all astonished, and secondly I liked it. And I have to read it to you. Where the mind is without fear and the head is held high, where knowledge is free, where the world has not been broken up into fragments by narrow domestic walls, where words come out from the depth of truth, where tireless striving stretches its arms towards perfection, where the clear stream of reason has not lost its way into the dreary sand of dead habit, where the mind is led forward by thee into every widening thought and action, into that heaven of freedom, my Father, let my country awake. I find there many, many similarities to international collaboration, to international aspects of particle physics, and to particle physics and the way we do research itself. The Tagore met more than one scientist from Europe. In 1929, Heisenberg was on a trip in India, and he, as far as I know, was invited to the home of Tagore. And they discussed there, and Heisenberg is quoted with this interesting statement. After the conversations about Indian philosophy with Rabindranath Tagore, some of the ideas of quantum physics that had seemed so crazy suddenly made much more sense. And the kinship between the ancient Eastern teachings and the philosophical consequences of the modern quantum theory have fascinated me again and again. So this shows again what philosophy and natural science can bring to each other and can be very fruitful in the progress. Why Heisenberg? Why do I mention Heisenberg? Because Heisenberg was a crucial person concerning the birth and the realization of CERN. And you see him here as the CERN from the left at the very beginning, in the mid-50s, at the very beginning of CERN. And Heisenberg was the German delegate who signed the CERN Convention. So CERN, as you know, was founded in 1954. At that time, it was going beyond national borders. Since 2010, it's going beyond regional borders, because science is global. And today, scientists from all over the world are coming to CERN. And you see here in different shadings all the connections CERN has to other countries. And what you see is that there are very few white marks where CERN doesn't have a connection to. In particular, I want to point out the associate membership of India. And here I want to mention my colleague and friend, son, Vikas Singha, who was one of the driving forces behind that achievement of India becoming associate member. And I want to take that occasion also to slightly delayed, by only 2 years delayed, congratulate you to your 75th birthday. But 2 years in our age, because don't matter very much, I have the impression. So these connections with all the countries are best illustrated, to my mind, by the young ones, because they are our future. And that shows before the pandemic, the summer students in 2019. On the top right, you see the crowd of young people. And if you would count, add all the numbers up, you reach a number larger than 330. It mentions so many young people flowing into CERN in this summer, enjoying science, enjoying the collaboration. It is a fantastic exercise. And that also brings people together from the early time onwards. And they come in order to learn about the mission of research infrastructures and then to support these missions. And I see 4 missions of research infrastructures. Definitely, clearly the research, to push forward the frontiers of knowledge. Innovation. We need to develop new cutting-edge technologies. But then, very importantly, education. To train scientists and engineers of tomorrow. And fourthly, the outreach, to promote science in society. And I think it's obvious to everybody we have a very excellent example, and that's CERN. And here's my first key message. Today we have challenging periods, but all regions need to step up the support for research and innovation, so that we can ensure in the global competitive environment a sustainable development of science and technology, which is necessary for the upturn and the growth of everybody's economy. And research infrastructures are one important tool for that. And in particular, of course, they are vital for large-scale projects. Now, large-scale projects address fundamental science questions at the forefront of research and technology. And again, I have to say, an excellent example is CERN. Oh, I know that there's a large hadron collider with its 4 large experiments: EMS, ALICE, ATLAS, and LHCb. And these 4 large experiments, they are, again, a fascinating ensemble of people, and a fascinating example for international collaboration. ATLAS and CMS are the 2 large multi-purpose vectors, and each collaboration counts over 5,000 members from about 40 to 50 different countries. You see on the top right ATLAS, and on the bottom right CMS. 42 and 54 countries respectively. If you compare that, then you must say ALICE and LHC are smaller detectors. On the other hand, if you come from other science areas, they are huge detectors and huge collaborations. ALICE with 2,000 members, you just heard a very nice talk about the heavy ion collisions. And LHCb has roughly 1,500 members and is specialized on precision physics with hadrons. I think, again, this is international cooperation at its best. And let me again stress that these experiments are international efforts. Without the next step, would not have been possible. And the next step was the discovery of the Higgs boson. The discovery was now 10 years ago. I cannot imagine that it's 10 years since then. 1 year later, the Nobel Prize in Physics was awarded jointly to François Englert on the left and Peter Higgs on the right for their theoretical discovery of the mechanism that contributes to our understanding of the origin of mass of subatomic particles. And of course, that was only possible because the theoretical discovery was confirmed through the experimental discovery of the Higgs boson by ATLAS and CMS. Now, one thing to keep in mind here, and I come back to that later, the discovery was 48 years after the prediction. And it was only possible through global effort. A unique large-scale facility and the development of new technologies. However, the discovery is the easy thing. It's only the beginning. The question is still, is it the only, or is it one of many Higgs? One has now to measure in the years to come with higher and higher precision the properties of that particle. They could give information on dark matter and maybe some indications of dark energy. And I stick my head out that our understanding of the universe is changing. I just don't know on which time scale. But the research program at the LHC will last for the next roughly 20 years. Now, what has happened in the 10 years since the discovery? And this is a plot which illustrates what you can achieve already with the proton-proton collisions in these 10 years. It's a measurement of the Higgs couplings to fundamental particles. And that's from ATLAS. You see plotted are the couplings, the vertical and the particle mass on the horizontal axis. And checking the key prediction of the standard model. Is the Higgs coupling to particles proportional to their mass? And you see it is. And it's not open. And you see also the same plot here by CMS. It is already a fantastic precision achieved on the measurements of these couplings. So there's an accuracy often better than 10%. But there's not only the heat boson to be studied. There are also, of course, many other physics results coming out, and especially the precision measurements from LHCb. And one of the highlights of the recent winter conference is from slight flavor anomaly measured in LHCb. You see on the right-hand side plot of the branching fraction of B plus to K plus mu mu over the branching fraction of B plus into K plus EE, and that should be 1, should be the same. What LHCb sees at the moment is a 3.1 sigma standard, which is the sigma deviation from standard model. It's of course not yet a discovery, but it's a hint, because it's stably, as you see the development of the values, it stays stably on the low side. So we need additional measurements. There exist already data sets which will provide further information. But now LHCb has upgraded for run 3, and one can expect in the next few years exciting use here. Others in CMS, of course, can contribute with similar measurements. So the key issue is for the next year's precision measurements can possibly, hopefully, point towards new physics and the scale of the new physics. So what is the path forward? Well, it's given in the update of the European Strategy for Particle Physics, which sets out for 5 to 7 years which direction particle physics in Europe should go. On the left-hand side, you see specific recommendations. I don't want to go through all of them. On the right-hand side, you find high priority items. And in the middle, there's one important statement. It is the importance of collaboration between CERN and national labs. Now on the left-hand side, you see one line in red. That is, highest priority is the full exploitation of the LHC and the high luminosity LHC. And that's the LHC program for the next 20 years. This year, CERN is about to start the LHC again after the shutdown. It's a so-called run 3. And there were significant improvements on the accelerator and the detectors. And the goal is to approximately double the luminosity. For the big experiment, for 2 large experiments, there's even more potential for others than LHCb, because they have, due to the changes in their detectors, they have increased rate capabilities. They can accept more events. Then, in the year 26 to 28, there will be a long shutdown to upgrade again accelerator detectors with increased luminosity to be prudent by a factor 5. The final goal, as you see here, is more than 3,000 inverse femtobarn, which is roughly 20 times more